So, my name is Piotr Padlewski. I currently, as Barbara said, work in Google on Clang devirtualization. And today I'm going to talk about C++ optimization, because I guess everyone who writes code in C++, he writes the code because he wants to have good performance and be optimal, right? So everyone cares about this stuff. So, the plan of the presentation. Firstly, I'm going to talk about studmove and Rvalue references. Then I will cover something called universal references. Then noexcept keyword, and some cool data structures optimizations. So, what is Rvalue? So I will not tell you the definition of Rvalue, because if I would have to read the definition from a standard, it wouldn't be a good idea. So I will just give you some hints. What is it? So firstly, it's every object that is temporary and is unnamed is Rvalue. So for example, if you have number 42, it's Rvalue because it doesn't have a name. And for example, I don't know, array of characters with hello world or something is also Rvalue. Also, we can say like everything that will be no longer needed, we try to convert it to Rvalues. So those will be Rvalues also. And the other stuff is that everything that doesn't have an address is also Rvalue, but it doesn't work in the other way. Something that has address can also be Rvalue. So for example, 42, we cannot take address of 42 because compiler will complain about it. So what is Rvalue reference? So Rvalue reference is just a reference. It behaves like a normal reference, but what makes it different is that it only binds to Rvalues. And here we have this double ampersand syntax for Rvalue references. So how does it work? So for example, we have this function foo. So some unnamed string temporarily will bind to Rvalue. Another something that will be converted to string, and that will also bind to Rvalue, and something that's another function returns. This is all the same case. And of course, if we will try to put something that is not Rvalue, which in this case is a named string, then compile will complain. And so, of course, if only temporary objects will bind to Rvalues, then it wouldn't make any sense, right? Because it wouldn't make that much difference. So we need some explicit way to say that, okay, take this thing and then like make it Rvalue, or I don't know, to say something like, okay, take this thing and now you can steal from it. You can do everything you want from it with this. So and function called studmove is the thing that we want in this case. So why do we care about Rvalues? So look at this example. We have struct foo, and what we want to do here is we want to initialize member A inside the foo without copying a string. Let's imagine that the string is like so huge, I don't know, 5 megabytes or something. We don't want to copy it. So we have constructor that takes a string by Rvalue reference, and then we want to steal from this thing that we got and put it inside the string. And I guess who see a bug here? Only one person?
Well, you're making a copy.
Of course. Yes, exactly. So I want to avoid copies, but what I'm getting is I'm making copy. And this is one of the common mistakes that programmers after jumping into C++ 11 makes. So what is going on here is that we think that we will not copy there where A is initialized. But we are copying because temp is not Rvalue itself. It's just a reference to Rvalue. So it means that we have something that points to Rvalue. But we cannot steal just like this from this reference, right? Because, for example, if we would have more members, then we could initialize them with the same variable, the same reference, which is temp, right? And compile will, of course, not reject this, and everything will be fine. So here's, of course, making copy, and so what we have to do, of course, is to use studMove once again. So now we are saying like, okay, I have temp, which is a reference to Rvalue, and now I want to make this temp Rvalue itself. So I want to say like, okay, I have something that I can steal from it, so steal from it. And now everything will work fine, we will not have any copy. And it works, of course, because string has a constructor that takes another string by Rvalue reference. So what studMove does? So it turns out that it doesn't move anything. It says that it moves it, but it's only the name. And what it only do is it takes the expression and changes it to Rvalue. And so as you can see, is just a static cast of thing. And what is very suspicious here is, does anyone see anything suspicious in definition of studMove? Yeah.
Well, one thing is you've already told us that ref t, the parameter, cannot take an L value, but you used it and it works because this is a template.
I will cover it.
Okay.
Yes, of course. So what is very weird here is that, wait, so studMove is taking something by Rvalue. So then why is taking something by Rvalue? So does Rvalues will work for with this or not? So let's see this example to see is it really works or not. So if we take this code and we'll compile it, as you can see, I put Rvalue firstly to the foo, and then I put Rvalue, and it turns out that it compiles. So, and it's like, what's going on, right? I have Rvalue there, and the only thing that changed is that we have template, and this is the only thing. So, and it turns out that this thing is not a bug, it's a feature. And we want to have it because we want to write functions that are generic enough to handle Rvalues and Lvalues in the same time as the same code. But the difference is that we want to know if someone passed Rvalue or Lvalue to this function. So how does it work? The same example, and on many websites you can find, so the thing is that going here is reference collapsing. And sometimes you can find something like this, that if I put Lvalue, like if I imagine that that type T is a reference, is Lvalue reference, and then I will get other reference, then it will just become normal reference. If I will get Lvalue reference, and then try to merge it with Rvalue reference, then it will still become Lvalue reference. If I try to put Rvalue to template, and I will try to merge it with Lvalue reference, then it will become Lvalue reference. And at the end, if I will try to make two references, if I will try to merge them, it will become something like this. But it's not how it works. So this is only that you can think about like this. The thing that works is the output at the right, but the thing on the left is wrong. So what tree is doing is going on is that if I have template that takes something by normal reference, then the type will be always just a single type. It will never be a reference. So, and of course, it will always become a normal reference because it's always single type. So it doesn't matter if it's if I pass Rvalue or Lvalue to normal template. But if I will put something to this function, then the type can be Lvalue reference or just a single type, as you can see here. So, and this is this is the way we can distinguish if someone passed Lvalue or Rvalue to universal reference. So what is the use of this thing? So imagine that we have struct foo, and we want to make a constructor that takes something, and then it either steals from the thing that it got and put it inside a string, or it copies to the string. And as you can see, some weird function called std_forward appeared. And what std_forward do is that if I will get Lvalue, then it will just don't do anything. And if I will get Rvalue, then it will do move. So, and of course we want to have it, because if you would just put stud move there, then in the example here, after constructing the object f2, then our string v will just magically disappear, and we don't want to have something like this, right? It's like it's very unintuitive, and it may cause many bugs. So, and of course, if I wouldn't put std_forward there, then of course we'll get copy each time. Okay, so std_forward is also, it doesn't forward anything. Okay, it's much closer to do thing that it does than std_move, and it's just a static cast, and it do exactly this thing.
Question?
Mm-hmm.
How much faster does this really turn out to be in practice using move and forward than copy?
I can always think about example that will show that it's infinite times faster, right? Because you can always like allocate, I don't know, 2 terabytes of memory and then copy it or move it, right? So sometimes it can be much faster, sometimes it can be even slower, but I will cover it at the end. So but the thing is that we don't want to, let's say, pessimize at the beginning, right? We want to write code that doesn't copy things when it doesn't have to. And the other thing is that using std_move is also a very nice thing to say, like, okay, I have this object and now I don't need it. So in this line, I'm just saying like, okay, I can get rid of it. Okay, and it can be it's mostly about code style, right? So, but I will show you benchmarks on the end. So, another example of universal references. Let's say we have some big structure that will store the same thing that we have in a constructor, and the constructor have many default arguments. And then let's say that we have other class that will store the previous class by a shared pointer, and by a constraint pointer. So it will say like, okay, I have pointer to this, and I will not modify it. So I will have many classes like this that will point to the same const extra param args, and I will have something that will mutate. So what we can do, so we don't want to write the same constructor that has the same default params. And what we can do is use C++ 11 feature called variadic templates, which is this ... thing in the constructor. So what is going on here is that the first argument is indexed, and the arguments after it is something like args in Python. It's just a list of arguments. In C++, we call it argument or type pack. And what we are doing here is that firstly we initialize index, and then we are making shared pointer here, and then we are forwarding each argument. So this thing like stood forward args ... will be changed during the template instantiation to the make shared pointer of stood forward of first argument, then second argument, then third argument, etc. So as you can see, we can write very generic code like this. But the thing that it's very important to mention here is that normally we wouldn't, we don't want to write things like this, especially with universal references, because we can generate something like 3 to the power of n, where n is the number of arguments. We can generate that much constructors, because each constructor will be different, right? If we will change one R value to L value, and if we will not pass one argument also. So, but I will tell you later how to solve it. But it also turns out that universal references are not so perfect. And in this case, we have function foo that we will try to make vector inside this function from the thing that we will get, and we want to put initializer list to this function. And it turns out that universal references cannot handle a case like this. And compiler will tell that he cannot deduce the type of the brace here, and it's because the brace like this doesn't have a type. This is very weird, but it's like you can imagine that we are using the same syntax to make some struct to put things inside a struct, right? So then it doesn't have any type. And what we can do is that we can use auto, which is another C++11 feature. And this is the difference, one of the difference between the template argument deduction and deduction of type for auto. Because auto can see that this thing can be changed to, that it can make initialize the list from things like this. And then we, of course, have to use move to move it in a place. Okay, off topic, defense programming. So, does anyone see a bug in this code? Who knows the boost tokenizer? Hands up. Okay, not many people. So this code looks perfect, right? It doesn't. We're constructing a substring there. We are moving it. We don't have to write move because it's temporary, and it looks very nice. When we compile it and we will run it, it can work or it will not work, and it is because tokenizer stores the string inside by a reference, because it is doing this whole token computation lazily. So each time I ask about iterator here, it will just go and search for a next token that can it can go. So what will happen here is we will bind a reference to the temporary object that will disappear after we construct the tokenizer. And it's common bug when you use classes like this. So we'll try to defend ourselves from things like this. And what we can do is that we can use another C++11 feature called static assert. So here we have, so firstly, the constructor of tokenizer is a template. And normally is just a template of a const reference. But what we want to do is that we want to take Rvalues and Lvalues and then reject Rvalues and say like it's invalid to construct tokenizer from Rvalue, which is true. And here we are. We are just using static assert, and then we are using a type trait called stud is Rvalue reference that will produce true or false at compile time, and then static assert will see this true or false, and it will fail or it will not. And this will be the the compiler output, which is very nice, right? Error, static assert failed, and it's invalid to construct a tokenizer from Rvalue, right? This is very nice template template error. It's like I would like to see something like this instead of backtrace on that much that I cannot scroll to the top. Okay, so let's go back to the references. So, as I said, there is a much better way to deal with cases, with many cases when we want to handle Rvalue references and Lvalue references by just taking by value. Because the thing that we want to do is we want to copy something, or if we can avoid copy, then we want to avoid copy. And as you can see here, we are just taking something by value. So in the case that it will be Rvalue, then it will be moved to the string s, and then we will move the string s to the s underscore. But if we will provide something that's Lvalue, which is a case f2, then everything will then we will have one copy, and after the copy we will move things down. So instead of doing things like, okay, I taking Rvalue or Lvalue, and then okay, I forward it later, and in next I'm taking Rvalue or Lvalue, and at the end I'm just checking like, oh, okay, so I will move it or I will copy it. We want to just make it at the beginning, right? We want to, if the copy is, if we have to make a copy, we will just make it at the beginning, and then we will just move it down. So, if of course type that we take by value has a move constructor, and the copy is unvitable, then we should pass something by value. And constructors are just a regular place that we want to do things like this. And the other thing, as I said, it also solves the problem with these variadic templates, right? Because instead of having that many functions, we will just take everything by a value, right? So let's imagine that we have function, and some programmer firstly said like, okay, I'll have string that I copy, and then I'm not modifying it inside the function. And then after this lecture, he thought like, oh, okay, so I have this string, so I can move it inside the vector, right? And the thing is that I don't know if it's better that it compiles, or if it's worse than it's making copy here. But the thing is that it's making copy silently, and we don't know about it. And it makes sense, right? Because we have something that is const, we declare it as a const, and then we want to modify it somehow using the studMove. But of course, studMove doesn't modify anything, right? It's just taking the expression and changing it to Rvalue. So what was wrong here, right? why does it compile and why we're making copy? Does the stud move didn't work or what? So it turns out that stud move did work, but it just changed the type to something like this, constring ref, which is something that's, yeah, it's Rvalue, but we cannot take advantage of it because it's constant. And no function you will never see function like this, right? Because nobody wants to take something by const ref. It doesn't make any sense. So the thing is that pushback, we have two pushbacks. One which takes something by const Lvalue, and the other one that takes something by Rvalue. And of course, we cannot bind const string ref to the string ref because we'll just get rid of const. So it will get bind to const string ref, and of course we don't have the constructor for a string that takes something with const string ref. So we'll have to make a copy. Okay, so we are getting to the very important question: is to move or not to move? And we will start with returns. So I guess everyone that started to using move just came up to the question, like, I am returning something by value, and should I move it or not, right? Because it seems that, yeah, I should move it, right? Because I'm getting rid of it and it will be faster, right? So the answer to this question is something called return value optimization. So return value optimization is optimization that was used like many years ago, before C++ 11, and what it do is it's instead of constructing this object inside the function and returning it, it just takes another pointer and construct it outside the function, right? I will show you. I will explain it more in a minute. And you could ask also like, does it change the behavior of the program? And the answer is yes, it changes the behavior of a program. So and normally C++ standard says like you cannot optimize and change the behavior of program. So for example, if we will have a constructor that says something like hello world or something, then instead of having like 3 hello worlds, after making this optimization, we get 2 hello worlds, for example, right? So the output will change, but it's good because standard said that we can do this. So it's the exception of something called as-if rule, right? And as-if rule is the thing that it has to have the same behavior as if all the requirements of the standard have been fulfilled. So how does it work? So let's say we have example like this. We have struct foo that have a constructor of 2 integers. We have some methods. We have some other function that takes it by reference. And we have the function that will return the thing. So, and we'll call some method on it, and we'll call some function with this object, and then we return it. On the color side, we'll just take it from the RB4. So firstly, of course, there is nothing like methods there is nothing really like a method. All methods are just function that takes this pointer by a first argument. So of course, constructor will be changed to function like this, and on the color side, we'll do something like this. We'll just, I cannot express it in a C++, so I said something like this. We'll just make take some memory for struct foo, but we will not construct it yet. And then we just pass this pointer to the function, and the function, instead of taking 0 arguments, we'll now take 1 argument more. And it will be the argument like puts result here. And instead of returning something, it will just return nothing. So what it do is on the beginning of the function, it just constructs the object, like it calls the constructor that we wanted. Then we can call some method, we can call some function, it doesn't matter. And then we return a semicolon, right? So now when we know how RVO works, let's look at some examples. So simple class that will just output the constructor calls. And let's try with something easy. So we have var, we return unnamed object, and then we get output like this, right? We just construct one object. And as we can see in the code, we are constructing two objects, right? So RVO works. And of course, the question is, what will happen when we will move? And it turns out that using move, in this case, will make it worse, because we'll construct another object, and then we'll move it to new object. So it will not be so bad, right? Because we are moving things. But imagine that we don't have a move constructor, then we will just copy things. So another example, we just construct object, call some method, and return it. So it doesn't make any difference, right? We will just create one object. And of course, if we will try to move it, then we will get additional constructor. So let's try with some branches. So if p, then we return, and else we'll first call some method and then return, right? And of course, it doesn't make any difference because these returns will be changed to return semicolon, right? So of course we will get good result. So let's try something harder. So what do you think? Can a compiler handle it? Hands up, who thinks that a compiler can handle it? Okay, who thinks that compiler can't handle it? Okay. So I will tell you that GCC cannot handle it, but Clang can. Yay. But so as you see, it's like it doesn't make any difference, right? Because we are constructing foo, which is unnamed object, but Clang see that, yeah, I could just construct the object before the if statement, and then just name it, right? It was in the previous example, right? So, but the thing here is that GCC couldn't handle this, but it moved object, right? It didn't copy it, which is very important, right? Because it means that if the compiler cannot, because we don't know if compiler will handle our function or not, and so we see that if it cannot handle the function, then everything will be moved, which is very nice. And it turns out that, yeah?
I'm sorry to interrupt you, but it's because bool is a very simple type here. If p had side effects, Clang couldn't do that optimization.
Yeah, I think so. But most of the time we are optimizing simple codes, right? Yes?
Well, I believe in this case, because the two code paths are completely disjoint, like no matter whether p is true or false, or even if it had side effects, we never actually construct anything into the return slot until we've made that choice. You know, we don't need to have two different things living in the return slot at the same time. So you should always be able to do it in this case. What you wouldn't be able to do is if you said foo A, and then if p returned foo, else return A. Right? That you definitely couldn't ever return that up.
Yeah. Okay, so the thing is that compiler is good guy, and it moves stuff if it will not handle the RVO, right? And this is some nice thing that say that is true. So let's play with initialize the list. So again, we have the two new constructors. One will takes L value reference to initialize the list, and second that takes value reference to the initialized list. And then we are saying something like this, right? Return, and then these braces. So, what do you think? Which constructor will be called? So, who thinks that lValue constructor will be called? Hands up. Okay. Who thinks that rValue constructor will be called? Okay, some hands. So, who thinks that some other, maybe, I don't know, something else will be called?
It may be a conflict.
Conflict? Like, so you think like ambiguous?
Yeah, ambiguous, because an rValue can go to either of those. I don't know which one.
No. It's like, if you have rValue, then it always goes to rValue.
Okay.
Yeah, it wouldn't make any sense, right? Because then we would have only object that can be moved or can be copied, right? And it turns out that it will be the third option, right? It will just call the default constructor because this one is not initialized list.
Oh, yeah.
And I got this one also. I didn't. I forgot about this one. Okay, so let's try with real initialized list like now. So we will get rValue, which is very nice. But let's try this one. We get out of v, it will be the initialized list, and then we return it. So what do you think? rValue or lValue? Hands up, rValue. Okay, lValue. Too many people don't know. Okay, so it turns out that lValue will be called. And this is something that we don't want, right? Because as you can see here, it's like, yeah, we are constructing foo from a v, but the v can be moved very easily. Like we see that scope ends and things like this. And what changed here is that instead of returning objects of type foo, we are returning another type, which is initialize the list. And this was the only one difference, right? And it turns out that there is this small bug in the standard. Let's say that bug or not, that compiler cannot handle it. It's the standard said that it cannot optimize based, it cannot just optimize it, because what's happening here is that it's firstly making it makes object foo from a v, and of course we didn't say move v, so it will just copy it. And of course, if we will move it, then we will get rValue. But the thing is, I really hate return std move, because, yeah?
I was just going to say, this is something we have fixed, I think, in C++ 14. I don't think any compilers fixed it up yet, but...
Mm-hmm. Yeah, I heard about that. They were trying to fix it.
17 draft. I don't think 14 has it, but 17 will.
So this was a bug then?
It wasn't bug.
Defect.
Is that?
Unwanted.
Yeah. Yeah, the other thing, I guess they fixed the thing that if you will say return std move of something, then then we will not get cases like this. Right? Oh. Yeah. So if we will say like return std move, then it will just it will get output like this. I'm not sure about it, but I heard that they were working on it. So, but so I don't know how about you, but I don't like return std move so much that I rather use something like this, just because it's more explicit, and it says that what we are doing here. So it says like, okay, we are constructing the object f, and then we return it. So we have to use std move, right? And this can happen like many times. For example, if we return boost optional, which is object that stores something inside, it copies thing inside the thing. So it will return. If we will try to return boost optional and we will return just string, then it will get copy. But we don't want to do this. Okay, so the other example, initialize a list or just constructing object. And again, Clang is awesome, GCC not so much. But to say in the defense, GCC could handle one of the case. It didn't handle the every branch, but it handled the case when we just return initialize the list. Okay, and what happens if we'll construct two different objects and then return one of them? And in this case, compiler cannot use return value optimization because, for example, what if constructor of foo would make put something on the output, right? Then compiler cannot do this optimization, right? Because we have to construct two objects. It's like we just cannot skip one construction. So summary: we never want to use return stud move because even if compiler will not be able to perform RVO, then it will just move it without our help. Unless, of course, we are returning object of different types, but we can handle it without return stud move. We can just create object. And if we want to make sure that RVO will work, then we should return the same objects in all returns, right? As you can see, GCC couldn't handle all the cases. So if we want to help GCC, we should do things like this. And of course, it's always important to make sure that we have a move constructor in our object, because if RVO will not happen, then we want to move happen. Okay, any questions about moves and RVOs? By the way, you can ask questions just during the talk, because I wouldn't like to go to the beginning at the end.
Just the statement you made early on that move doesn't change, that it didn't call for a constant value, it wouldn't call move. And you said because you were questioning why it wouldn't, because it's not modifying the value, but most moves do modify the value. They don't, they're like in a string, it's modifying the string address and length to be 0. It's
yes, of
it's
course.
setting up the new one, so
yeah,
it really is modifying.
Yeah, of course. So that's why we cannot just move it. We cannot steal from the object that it comes, right?
Yes.
And that's
I
why.
thought you were questioning that.
No, it was just question that I answered.
Okay.
Yeah?
Just a comment, and I think Arthur discovered this as well. If you do a return print, as in the curly braces open, expand an argument back, and then parentheses close, it will actually depend on the length of your argument back, whether it controls the constructor or the initialized list version, which may or may not be what you want.
Okay, I didn't know about it, but
Yeah, stressful.
but either I don't want to search in the code for cases like this and change it. But it's good to know it. I don't know. I just don't like use braces as constructing.
It's just one more weird edge case.
Yeah.
A comment on the earlier comment about const R-value reference. You could, I suppose, in theory, define a constructor that took a const R-value reference, but it would be useless because you couldn't move any data out of the
Unless you would constcast, right? But
Yeah.
you don't want to do this. Yes. Okay. So noexcept. So this is a new keyword in C++ 11, and we can be thankful to C++ standard because they don't like to add new keywords to new standards. So we have three functions. First function maybe. It doesn't say anything about exceptions, so it can throw or not. We cannot just deduce it just on a declaration of a function. So we don't know about it. The second function foo says that it will not throw anything. And the bar also says that it will not throw anything. So what is the difference? The difference is that in the case of throw, compiler have to unwind stack if someone will throw inside this function, because if the declaration of function doesn't say, and compiler doesn't check if anyone will throw anything inside this function. So you can throw things inside functions that are declared by throw, but then it will lead to called to terminate. And with noexcept, it will also call to terminate. But the thing is that you don't have to unwind the stack. Yes?
Is there any difference between noexcept and no throw?
There is no such a thing as no throw.
No throw is C++ 99. That's the same that
Is there anything like I never heard about C++ 99.
Yeah, it's just like throw but no throw.
Maybe some I don't know, some compiler initial thing. If it starts with underscore, it is. Okay, I don't know. I never heard about. Right. I don't know, Richard.
I'm pretty sure no throw is equivalent to throw open close.
Yeah.
I think it's exactly the same.
Yeah. But I don't know. I never saw no throw. So. Okay, and you would ask like, okay, does it make any difference to unwind stack and to not unwind stack? And I would say like, no, it doesn't. It makes it may make little small difference, because just compiler will not generate bytecode that will do this all stuff. So our code will be a little bit small, but it's not so huge difference, and we don't care about noexcept because of this reason. And the thing that I mentioned is that it doesn't matter if I would say that something is noexcept, we can always throw inside this function, because this is only declaration, right? And of course it's because we are in C++, not in Java. So the same class with some constructors that put something on the screen, and then a small code. So we are constructing a vector, and then we are inserting 3 elements to this vector. And I'm using here a function called emplaceback, which do the same thing as pushback. The difference is that instead of taking something by reference or by a Rvalue reference, it takes arguments and then forwards them to the constructor inside the vector. So instead of creating object and then passing into to the pushback, we are just creating object inside and place back, and just and create the object in a memory. So in this case we'll avoid some Rvalue some move constructors. So it turns out that if we run this code, we will get output like this. So first we insert first thing, then when we want to insert second thing, then a vector have to make more space, right? Because it has only one space at the beginning, or it differs from the implementation, right? But in this case, it was like this. So we construct one new element, and then we are copying things, and it's like, wait, why we are copying things, right? We just have old vector, new vector, and we would like to just move everything down, right? Why we are copying? And it's going on, right? Then if we put next element, then we have to make space for 4 elements. So we have to move or copy the 2 elements that are in the previous vector. So, and this is like, damn, we don't want these copies, right? So how we can avoid them? And the question is, why we are having those copies? So it turns out that vector have a strong exception guarantee, which means that if we will if we will change the vector, if we will push back to the vector, and if something bad will happen, if some constructor will throw an exception, or something else will, but some other exception will be thrown somewhere, then standard says that after the thing, if we will catch the exception that will be rethrown, then the vector will stay the same as before the operation that caused it. And imagine that we are allocating new memory, and then we are trying to move things. And in the 42 elements, the move constructor throw exception. Then we don't have anything to go back, right? We could try to move things back to the previous vector, but nobody says that it will not rethrown again, or what about the element that's thrown, right? So what we have to do is, of course, vector have to copy things. Yes?
But there's a simple reason for the need for the copy. Objects can have self-references, so you can't move C++ objects freely.
This is not the case. I mean, it's not about this. Okay, I will just say why. I don't think that it makes because moving shouldn't make shouldn't break it, right? If we will just move objects and we'll move every object, then
I see. You're talking about the move constructor, not bit splitting. Okay, sorry.
Okay, so how we can fix it is we can say, not yet, but the other thing is that vector is using something called move if noexcept, which is a function in standard, so we can use it. And what it do is it moves if the constructor is declared as noexcept, or we don't have any copy constructor. So for example, if we will have a unique pointer, and imagine, unique pointer doesn't have a copy constructor, and imagine that it's not declared noexcept, then just standard says like, okay, screw it, I will just move it. So we can fix it by adding a noexcept keyword to this function, and then we will get moves, right? So, and this is the thing that we cannot just change the implementation vector, right? So this is the only way that we can prevent copies like this. The other thing is that we can use default. And this is like extremely awesome, because imagine that default wouldn't mark something as noexcept. Then people would start to not use default and write their own constructor that do this, that are generated by compiler, right? It's like and just mark it noexcept. But the thing is that it marks it as noexcept only if it can move all the members without throwing any exceptions. So if all the members move constructors are noexcept. And how does it do? There is noexcept is not only the keyword like this. It's operator like the one that you see. So we can put a boolean to the noexcept and say like, okay, if the boolean is true, then noexcept will stay, and if it's false, then it's the same as noexcept would disappear. So for example, if we have let's say that some algorithm have to know that swap will not throw any exception. So we can check if swapping members of a pair will not throw any exception. So we said like noexcept of first and p first, of swap first and p first will say like true or false. The second noexcept will say like true and false, and doing add will do the true or false, and then we'll stay with the last noexcept, which will be like noexcept true or false, which will be noexcept or nothing. And in this way, we can also check if our move constructor is declared as noexcept. So, summary. We should use noexcept for documentation. So, of course, if something doesn't throw, we can mark it as noexcept, and it's much better. It's much better than using this one. It's much better than using throw. Always use noexcept instead of throw because it's just better. And if you say if you mark the move constructor as throw, then it will be not noexcept, right? So we will not get all these features that we want. The other thing is that, of course, if you want to generate default constructors, we can use default, and we don't have to think about this noexcept things. And of course, we want to always define constructors as noexcept. Of course, unless they throw something. Because if they throw, we don't want to mark it as noexcept. And the most common case is if we allocate some memory inside. We don't want to mark the function as noexcept. And the other thing is that if we are not sure if the function will throw anything or not in the future, then we shouldn't mark it as noexcept because someone in the future can think about it like, oh, this function will never throw, and then we change the API and it's starting to throw something. So this is very bad. Okay, small digression. What will happen if we would move this question?
Yeah. Why can't the compiler add noexcept for you since it can determine it statically?
Because it's not in the standard now. So I guess there was some proposal about something like noexcept auto, which will do the same thing. I guess the much better thing would be just to not write noexcept auto. It would be, but the thing is that it could only work if we have definition, right? So it will not work if we firstly just declare function and say noexcept auto, because compiler in this translation unit doesn't know if it shows anything or not, right? So it will of course work in a template, but in normal thing that we declare function and then define it will not work. Okay, any other question about noexcept? Okay, so back to the digression. So what will happen if we will move something to ourselves? So of course, two things can happen, right? It can be either the vector will just disappear, right? It will shrink to 0, or nothing will happen. But of course, C++ is a quantum machinery, and both things can happen, right? So of course, it's undefined behavior. And it's like, and you wouldn't think about it, right? It's just a small move. And the other thing is that...
Why isn't the operator assigned defined properly so it will compare this to the R-value reference?
Yeah, but the thing is that the standard says that if we will do this thing, then it's undefined behavior. So I guess even if you declare... Okay, I'm not sure about this one. I guess even if the standards say that this line is undefined behavior, then even if you would compare the thing, we can break your code as a compilers.
Well,
okay.
If W equals W is not undefined, why would?
And yeah, the other thing is that I don't know why they did this, but
what seems to be the problem to define?
I guess they just think like nobody will move its thing to itself, and they will just check it in all algorithms that can do this. And this is like, yes?
To show that isn't the case, there have been STL implementations that got, I believe, random shuffle wrong where they couldn't read the case itself.
Yeah, I heard that there was some bug.
Yes.
That there was bug like this.
So if the STL gets it wrong, you will too.
Yes.
Can it be that once you move the object, it may become an unassignable thing?
Well, in this case, you get an operator equals over R-value reference to the vector.
But if the right-hand expression moves it, now the left-hand expression may not be puttable. It may be in an inconsistent state itself. Maybe.
Or you mean if there is a more complex expression?
Yeah. Just guessing.
Yeah, the thing is that, you know, if the implementation of move constructor is doesn't check this, then it can firstly like assign a pointer to that pointer and then make that pointer 0. So in the most of the case, it will just make we will have a leak of memory here, and the pointers will be set. The pointer will be set to 0, but it's undefined behavior. It's like bad things can happen, right? Yeah.
I think to clarify, self-move is not undefined behavior. It's just undefined for all of the classes that are in the standard. You can define your own class that handles self-move.
Yeah, of course.
In the same fashion, but vector does not.
Yeah, we can if this is a vector and then format your hard disk. Yeah, any other question?
I was just going to say, this isn't actually specific to move assignments. The general rule for the library is you call any library function and given an R-value reference to something, you are telling it, this is the only way to get it to stay. If there's some other way of getting at that thing which that function can see, then it's not required to check that.
Just one more comment. In the example with the vector and then placing them, if you know how large the vector is going to be, reserve the necessary amount of space, and that's a nice optimization because you won't have to resize. As in the vector itself won't have to resize every time you add place back.
So let's go. So let's move some containers. So many times we have something like some large vector that stores everything, and then we have some small vector that's caching things, and then it just copy everything to the big vector. So we would like to move all the stuff. So firstly, we can copy the stuff. So we can use studCopy, which is a function that takes 3 iterators. The first 2 is a range that we are copying, and the last one is iterator when we put out iterator where we put the things. And studback is inserter is something very magic. It's something that wraps iterator, and each time we take the star of the iterator, it just copies the thing. And I don't know how about you, but when I use back insert, it's like, yeah, that feel. But there is much better to do things like this, because we can use a member function called insert, which takes first pointer is where we want to put the things, and two other iterators is like the range that we want to copy. And the difference is that the copy one will just iterate over the container and then call pushback each time. So it will reshrink each time we don't have enough space. And the insert will just see like, oh, I have those 2 iterators. I have that many elements to copy. So I don't have that much space. So I will firstly allocate the memory and then we'll copy everything. So insert is faster. But we still are copying things. We want to move them. In the first case, we can use studMove, which it turns out that there is a studMove that takes iterators, which is very nice, right? So it does the same thing, but instead of copying, it just move. But it's like, I don't know which one. Sometimes this one will be faster than these 2, or sometimes the insert will be faster than move. So we want to have something that is much better than every of this. So we want to have this something like insert, but that will move things. And there is no function called insert move or stuff like this. The only thing that we can do is that we can mess up with these iterators. And how to do this is we can use function called makeMoveIterator that will make move iterator. It will just it will make iterator that every time we ask about the about element, it will steal it from the old container and move it to the new container. And this is the best way to move some other container to new container.
Then your cache will be in an invalid state because nobody will do resize it back to 0. So all elements between cache at the beginning and cache at the end will be uninitialized memory effectively.
Yeah, but it's like you don't have to use cache. Of course, you should I don't know, resize it, or you should clear the cache after this operation, right? So, and the other thing is that of course we have memory allocated in a cache, but we will not have any elements inside it, right? So there will be no bug because of it. So some optimization that doesn't make any sense. Many times people are trying to find some code and try to optimize it, and they think that, yeah, I found something and it will make my program faster. But it turns out that in many of those cases, compilers are doing the same thing for them. So, for example, if we are inlining on our own, so let's say some programmer from, I don't know, ICMs or something. They usually put inlines everywhere because they think that, yeah, cost of call is is so expensive. I don't want to call things. I want to inline them inside, and I don't want to use macros, so I will just use functions and inline, right? It's like no, you shouldn't use inline for cases like this because compiler can figure it out better than you. Using E++ instead of ++E instead of E++. So I heard stories like, yeah, you should use E++, ++E instead of E++ because in the second case you are making copy. It's like, yeah, but compilers see that I'm making copy and I can just avoid making this copy. And in the cases like integers and iterators, it doesn't make any sense because compiler, most of the time compiler can take a template inline thing, like if we have iterator, and see that, oh, okay, I'm making the copy of this thing, but I don't have to. So sometimes it can, of course, it can matter if we would have some stream and the definition will be somewhere in some other translation unit, then it can matter. But in most of the cases, it's of course it's not worth to look for cases like this and change the code. But I don't say that using E++ is better than ++E. It's your choice. So bit shifting instead of multiplication division modulo. The other side is like, yeah, I'm just doing this tree stuff, and here I just multiplying it by 2 and dividing it by 2. So I just bit swap things by one place because it's much faster. And it's like, yes, it's true. Bit shifting is faster than making multiplication and division. But compilers see that, oh, I have integer and I'm multiplying it by 2. Oh, so I can swap these bits. Ah. Yeah, so it's like, you don't have to make your code look awful just to not get anything, right? I'm starting end to the to other value. This is something like I said maybe, because sometimes it can matter, but most of the time it doesn't. Because most of the time we are dealing with templates, and most of the time taking the value to the other thing will not make so much difference. And the other thing is that if we are using for loop, the derange loop in C++11, then it do these things for us. So we don't have to write our own for with iterators and just take the end to other value because, I don't know, the range loop doesn't do this. Using register and restrict. In C++11, using register and restrict, it's like putting some more space. Because register is like, you are trying to say to the compiler, yes, yeah, take this integer and put it in a register. And he's like, I know. It's like I'm compiler, right? And the other thing is that so it matters, like, I don't know, in C++ 17 or something like this, when the C++ was not even there, right? But now it's like the compilers are too good to to care about things like this. And restrict is a keyword that says that we have two pointers. They are not aliasing, but the definition of aliasing is a little bit broken in C++ standard. So compilers doesn't care about that. the restrict keyword. Using weird type traits to change function signature from T reference to just T. So imagine that we have vector, a suit vector, and we have function called pushback. Normally, it's defined as take integer by a reference, right? It's like tref. But compiler can see this and see like, oh, so we are taking this by a const reference. But this is integer, so it's better to just copy integer than to take pointer to it that could be much larger to it and make some new indirection. So we just change the definition for you, right? And compiler can do this, which is very nice. Okay, other example. So imagine we have code like this. What we are doing here is we have two loops that are going from 1 to n. So we have quadratic thing, and so what we're going is like we get n from the arguments and value from arguments, and then we are trying to find the value. So in the worst case, we will do n square operations, right? And if we will call this program with output like this is 2 to the power of 9, and this is sum from 1 to this is a sum from 1 to 10 to the power of 9. And if we will compile with GCC and Clang, then what we will get is that Clang runs it in 2 seconds, and GCC will run it in about 42 years. And so it's like, what is going on here? And it turns out that Clang is very good at optimizing loops like this. And it sees this loop, and it do the math stuff, and change it to the equation. So, we could change it to the equation, right? And it's simple. Everyone knows equation for this. But if we will have like some very nasty equation, then I don't know. I would be too lazy to put it even to the Wolfram, right? So it's very nice that compiler can do this for us. Okay, so let's go to some more containers. So difference between set and unordered set. So of course set has sorted data, and unordered set doesn't have sorted data. And set in theory can take less memory because it allocates each node for each thing that we put to the set. And the unordered set is a hash table, so it can allocate more memory, and we can have blanks inside. So and of course unordered set is much faster than set. So my question was like, should I use? So in many cases we want to put something in a set, and then we want to do something with this, and we want to, for example, have after this whole after we put things in the set, we want to have it in an ordered way. So my question was, is it faster to use unordered set and sort it before doing these things? So I checked it, and this is the code that I was doing it. So we have stud set. We put random things inside because this is how we usually put things inside the set, right? They are not in the right order. And then let's say that we are iterating over it and take something. And let's say that here it has to be sorted, right? And we will do the same thing with unordered set, but before we will iterate it, we will just copy everything to the vector and then we will sort it. Okay? So I check the times, and it turns out that it looks like this. The red one is ordered, so it's set, and the green one is unordered. And it turns out that the unordered set, for cases like this, for integers, is 2 times faster. Very nice. The other thing, the same thing with map. So you have map and unordered map. Here we are making a vector of pairs and sorting it, and we'll get the same result. But we can get much better with map, because in many cases, instead of having the whole thing, the k and the key and the value, we can just take the thing that matters to us. So we can only take, for example, this stud vector of values, then reserve the thing, put everything inside, and then it will be a little bit faster. Not so huge difference, but still. So okay, so yeah.
There's an example with a set where we say that the unordered set and then we sort it faster. Is that just the current implementation of that of the set and unordered set that's causing this, or are you saying that this is an inherent feature and it's going to remain like this forever?
I would say that yes, it's a because of implementation. But the thing is that you should, if you want to have set faster than unordered set, then you screwed up your unordered set that much, because it's like unordered set is a hash table, and it's much better to cache it, and unordered set will be almost always faster than set. So it's just about how we access memory in the computer.
What I'm asking is this: supposing I want ordered, am I better off writing code with ordered set, or are you saying that you're better off using unordered set followed by sort? Because once I write the code, it might be long-lived, right? And the implementation can change over time.
It depends. So no, it's like unordered set should be always faster. And I don't know, maybe if someone will solve some NP hard problem, then set will be faster. But it's like, no, if the architecture of computers will not change, which we don't see it right now, it's like unordered set will always be faster. Yes?
Would you please show again the 2 comparison charts for sets and for maps?
So they look almost the same.
Sets, okay.
Yeah, this is unordered set.
What operation is being measured there?
The whole thing is being measured. So where the inserting this code, this function is being measured. So inserting the thing and then iterating over it.
Okay.
And in the case of unordered, is inserting, then copying everything, then sorting everything, and then iterating over the vector.
Can we see that chart, please?
Chart? This one?
No, the one for maps.
Ah, okay. So it looks.
Okay, and there was another one on the third entry.
Yeah, so the yellow one is when we don't copy everything, and when we copy only the thing that matters.
And what is unordered too?
It's a thing that's when we don't copy everything, when we just making vector of things that matters to us, and then we reserve thing and we are iterating over it. But this case is like it doesn't always happen many times. Yes, anything else? Any questions here?
Could you go back to the slide where you insert the elements directly? So you're inserting elements in an order.
Yeah.
Does it matter if these are random elements? So I suppose this is happening because
yeah, but the thing is that in the map we have everything by a key, right? So it doesn't matter that I am inserting the values in order. It's
no, yeah, I understand, but like these are values from 0 to size. I'm saying is that like if these are very random elements,
This,
If the hash value is not uniformly distributed,
if the hash values are not uniformly distributed, perhaps this will change, because now the entire map is filled with elements, so iterating over the map isn't very expensive, because each key is present, each bucket is present.
Yeah, but it's like I'm inserting the random things, right? And the thing is that the values are unique. It doesn't make any change, because what matters is the keys, right? So and most of the time I'm inserting to the map or set some in the random order, right? So here it doesn't matter if that I'm inserting the random things. Those are random things, right? So
keys are random.
yeah.
A question might be, is the map, the binary tree, becoming a linked list degenerate behind the scenes? But it's not true,
never,
because they are all balanced red trees,
of course,
wise, so it doesn't matter.
It's the map. Give me 1 second.
Keys are random. Values are.
Okay. That was fine.
Okay, so let's move to the boss. This is the one of the interesting thing I have to show you. So I had a story that one time I was writing some small program for a competition, and I wrote code like this. That it has a constructor of vector of sets, because it was like I couldn't use C+11, so I had to use sets. And I took it by reference, and then I copied it to this vector. And then I just posted it, I just sent it, and after this, I still like, oh, I'm making copy here, so I can avoid it, right? And the program was so small, so I added just a reference, just to avoid copy. I know it's bad, but in C++ 98, there is no much you can do about it. It's hard to do something better. So I added this only the reference, and the result was that the one with reference got 2 points less, like 20% points less, and it was because of time limit. So then my thought was like, damn, references are that slow or what? It's like I was copying the whole thing, right? And it was faster than taking by a reference. Like, why? So I tried to answer this question. So I started benchmarking other things. So I made something like this template to check how it works with different containers. So what I'm doing here is I am just iterating over some container, and I'm iterating it till the reads will go to 0. And I have to do something with the container, so optimizer will not, just wipe out the whole 4. So I just check if the value from the container is less than equal than some random number, and then I just add the value. And some other helpful functions, so it will work with map and other containers. And of course, in the version 2, where I copy things, I will just take it by a value, not by a reference. And to make it harder for an optimizer, of course, I will define this function. I will declare a function like this and define it in some other translation unit. So it will not be so easy that it will be just template and he will see what's going on. So of course I will try to see the difference between taking by reference and then or just taking by value and moving it to inside. So I will just take copying on the first place, and then I will move it. And I will only measure the difference between those two. So I will not measure the insertion of the thing and construction of the thing. I only measure the how much time I spent during the during the iteration of the container, and in the other case, how much time I spent during the to copy the whole container and to iterate over it. And it turns out that I got something like this. The red one is when I make a copy. The blue one is when I have a reference. On this axis is time that the program took, and here is like how many elements how many reads I had in this container, and it is for 1 million elements for map. So as you can see, what I got is like, yeah, if I just copy container and not do any reads, then I will have to pay this to copy it, right? And this is constant because the size of the map is constant. But as I will make more reads from the container, something around 2 millions, so I have to just iterate over the container 2 times, and it will be like the same amount of time. And then if I will go more, then copying will be faster than taking by reference. So this is like, wow, this is weird, right? So let's try with another container. So this is like how an ordered set looks like. It's not so nice, but it also differs from other CPUs. So what I got on other laptop on i5 was something that was more like this on an ordered set. So let's try with an ordered map, and again I get something like this. So I said like, yeah, so okay, I having reference, but I can avoid copy, right? I can just not pay for the copy and having the object by and taking the object by just referring to object by value, not by reference. Okay, so I tried to move things, and it turns out I got something like this. And the green one is a move, so it's the same as when I take it by reference, right? And it's like, it doesn't make any sense, right? I didn't pay for a copy, right? But still, in the summary, it was slower, right? The iteration over the thing was much slower. So, and the other thing is that, so I checked how it is for vector, because if the reference would matter, then it would matter much more for a vector, because we don't have that much indirection, right? So, and it turns out that, again, it was the same as we would take by reference. But in a vector case, there were no, the iteration was the same time. I just had to pay this for a copy, right? So references are not slow. This is not true. Something weird is happening, right? Some magic is happening during copy, and I have hints. Does anyone can guess what is going on?
Cache locality.
Exactly. So of course, what is going on is a cache, and what we get is cache misses when we are taken by reference. So how does it work? Imagine that we have map or set or something like this, and imagine that after some insertions, our map looks like this. Because we were inserting in a random order, then the thing that the pointers were pointing to can be in the random places in the memory. So when we are trying to go through all the elements of this set, then we will get like, okay, get me this pointer. Okay, I have to go to the memory. Okay, here you have. It's in cache right now. Okay, give me this pointer. I don't have it in cache. Okay, I will go to memory. And then after 200 cycles later, yes, you have it. Okay, give me this memory. It's like, yes, you have it in the cache. Nice. Give me this pointer. Okay, I still have to go to the memory. And each time we have to go to the memory, of course, our program will go slow because we want to have everything in cache. So after we copy, the most likely thing will happen is this, because we'll be going to we'll copy the things in the order of the map, and allocators like to put things that are near each other in the memory. So he will firstly like allocate this one, and then go to the next elements like, okay, allocate 3 for me, and it's like, and he will say like, okay, I will try to do it near this one, and if we will manage to do it, then we'll have something like this, everything near each other, and then everything will be cached. Everything will be will not have to go to the memory. Everything will be cached very nice. And the other thing is that our map can balance a little bit, because before copying, it will be balanced, but it will be not balanced perfectly, because of course black-red trees are not balanced perfectly all the time. There could be differences like this, and of course we can change it to a case like this. So things like this happen. So let's check if we understand the problem. So let's try what will happen with list. So here we are inserting elements on the front or on the back, and again we are measuring the same thing. So what we will get is something like this. So it's very similar to vector, right? But the cost of copying is so huge. So someone could say like, yeah, but the thing on the map was sorted, so let's try to sort the list, right? And what do you think will happen? Something like this will happen. And if you check it, you can see like, oh, damn, copying so fast, right? But the difference is like, look at the time. There's like 1200 milliseconds in this case after sorting, and before it was something like just 100. So this is not about copy being fast. It's that after we sorted the list, everything was just, you know, we just made a random shuffle of the memory, right? we ordered the things but now when we are when we are iterating over this, then everything is somewhere else, right? So copy can defragment memory in that way. It can pack things together, and it will do it like this. And after doing copy, we will get less cache misses and performance boost. And of course, it's not like you should copy, but as you can see, it's like if you are using something very much, then it can really matter that you will copy it or not. So you don't want to avoid copies and all the time, which is not nice, right? Because we would like to avoid copies all the time because it's better. Like, you know, we don't make that much. We don't make additional. We don't pay this additional cost. But it turns out that's like, nope. Sometimes it's worth to copy. And the other thing is that in Java, for example, there is a way to call some garbage collector, right? And C++ doesn't have garbage collector. You cannot defragment memory just by calling some, I don't know, C function or something, right? So this is the only way we can do things like this. Small digression, vector versus list. As you can see, vector is much faster than list. So, and this one is for integers. It may vary if we use some big objects. But what I'm trying to say is that we should use vector as a default. And in which cases we want to use vector. So if we have sequential unordered data, so we have we want to store many things, but we don't care about if it's unordered or not. Then this is the best way to use vector. But you may say like, what about if I want to remove something from the beginning of the vector or from the middle, it will take like linear time, right? And it's like, and I would say like, no, you can do it in constant time, because you can take the last element, this element, swap them, and then remove the last element, right? You will get constant time. If we want to use something like a static set, so what we want to do is we want to write everything to the set, and then we want to find things inside. So instead of using set, we can just write everything to the vector. We can just call pushback, pushback, pushback. Then we can just sort vector, make it unique, and then we can find it using lower bound, right? So it will take the same. It will be logarithmic time, but as again, vector is much faster because it's cache friendly. Small set map with all the operations. So if we have like some small set, like I don't know, 100 elements, then we should use vector. We can do everything. We can just remove things from the beginning, everything. It will be just much faster. Even if we will do a linear search inside this vector, it will be still much faster than using set or map. Or if we want to have something like map that will index by integer, so we want to have something like hash map, and we can use also, like if we don't care about memory so much. And this is some example that how you can write this kind of map. And this is the easiest way. It's just to derive from vector. And you could say like, is it safe to derive from a vector? It doesn't have a virtual destructor. I would say like, does it matter? It's like, do you store pointer to vector or take it by reference and then call some virtual function in it? You never do this, right? So you can do things like this, and to make it safe that you didn't that you don't have something you don't have const reference, for example, to vector, and you're using this object, and then if you destroy the vector, it will make some memory leak. We can assert like this. So we can check if size of vector is the same size of this new vector. Of course, this is not perfect because they can have the same size even if they have if the auto-sorting vector will have more memory. But it's something that can save us. For if some nasty programmer will just see this new vector, it's like, yeah, I will just add some new data to it. Another thing is like why it's nice to have a function, a member function instead of some global function to do this, because that one is much nicer than this one. Okay, thank you very much. Let's go. So, is there any questions about doc or about copying and stuff like this? Yes.
You mentioned the restrict keyword.
Mm-hmm.
I've seen that matter in auto-factorization and it not being able to auto-factorize if it wasn't there.
C++ 11 or?
Yes.
Okay, I don't know, but it's like, especially when I would be firstly, restrict will be dangerous, right? Because you could say that it's restrict, but it will be not. The other thing is that, do you care so much about this? Like, if you will spend that much time to look all these places and put restrict there, you could write some edge code in that time, right? I guess it's not worth it, unless you are doing some very crazy optimization and you're finding some thing. I don't know. It's like I heard the story like that because the definition of restrict is a little bit broken.
Yeah.
Then compiler cannot just use it that much.
on that comment about when you were saying don't do bit shifts by hand for multiplication things. Not only can the compiler figure it out, it can figure it out better than you can. Because, for example, like on x86, there's some really interesting instructions that you can abuse to implement multiply by 12, 14, and 26.
Yeah, exactly. And the other thing is that shifting doesn't make the same thing all the time, right? If you have some signed integer, then shifting bits will not always multiply things by 2, right? So it's also dangerous. Any other comments or questions?
We can go ahead and take this over to the Tide House. Thank you so much, and thank you for being here at Google and coming to speak with us.